This is problem number 14 from 2016 advanced level paper. Uh, so here we have a water hyacinth bunch floating on water. It's on a still lake and wind is blowing. So they have given us three statements and are asking whether they are true or not. So let's first draw the free body diagram of this water hyacinth bunch. So I'm going to draw the free body diagram here. The first thing which is obvious, there's mass. So as a result, there's the weight of the water hyacinth bunch, and that's vertically downward. Let's call that mg, where m is the mass of the bunch, and it's floating. As a result, there's a buoyant force acting on the bunch, and that's directed vertically upward on the bunch. So let's call that FB. B stands for the buoyant force. And let's say that the wind is blowing from left to right. So I'll show the direction of wind over there. And because the leaves of this water hyacinth bunch are very large, what air molecules are going to collide with these leaves. As a result, there's going to be momentum transfer. There's a change in the momentum of the air molecules when they interact, when they collide with the large surface area of the water hyacinth leaves. As a result, there's going to be a force acting in the direction of the wind. So let me call that force F1. Okay, and since there's a force, it's going to accelerate along the direction of the wind, and there'll be a velocity for the bunch along the direction of the wind. Because of that velocity and it's floating in water, there's going to be a drag force, which we can say that there's going to be a viscous force acting in the opposite direction. Okay, so I'm going to draw the viscous force as F2. So these are all the forces acting on the bunch. There's a forward force due to the momentum transfer of the air molecules interacting with the bunch, F1. Fb is the buoyant force, that is upward. Mg is the weight of the bunch, and F2 is the viscous force because the bunch is moving forward. It has a forward velocity. So the viscous force, we can write that in terms of viscosity of water. So I can write viscous force F2. You should know the expression coefficient of viscosity, the surface area times the velocity gradient. Okay, so I'll write that as V over L. But here I'll bunch all the stuff excluding V as one constant. So neta times A divided by L, I'm going to bunch that as 1, and I'm going to separate out the velocity. So I can write F2 as a constant K times V. And inside that constant K, we have viscosity of the liquid or water. Viscosity of water is there. So that's how we express F2, viscous force, in terms of the velocity V. So let's write down Newton's second law along the forward direction for the bunch. So if I write F equals MA, F is the net force acting in the forward direction. So that's going to be F1 minus F2 equals mass times the acceleration. Okay, and what I'm trying to do is I'm trying to separate out v, or in other words solve for the velocity, because the three statements over here, you can see they are all asking about the speed, the velocity, the magnitude of the velocity. So that's why I'm trying to solve for the velocity. So F1 minus F2, I can write it in terms of velocity, k times v equals ma, and I'm going to solve for the velocity. So v is equal to F1 minus m times a divided by that constant k. Okay, so now I have obtained an expression for the velocity of the water hyacinth bunch in terms of the forward force, the mass of the bunch, the acceleration of the bunch, and k, a constant that has the coefficient of viscosity. Now let's look at the statements from A to C. First statement, magnitude of V depends on the rate at which the momentum is transferred from the air molecules to the bunch. So the rate at which momentum is transferred, in other words, the rate of change of linear momentum, that's the definition of force. Okay, so magnitude V pretty much depends on the force due to the molecules, and that's F1. That's our F1. So yes, magnitude of V depends on the rate at which the momentum is transferred from air molecules to the bunch, and that statement is correct according to our equation number 1. Second statement, so A is correct. So A is true. Statement B, magnitude of V depends on the viscosity of water. Viscosity of water is eta, and that's inside this K constant. And if you look at equation 1, in the denominator you have that K. So yes, velocity depends on viscosity of water. And we can further state that when the viscosity increases, the speed decreases. And when viscosity decreases, speed increases. So yes, magnitude of V depends on the viscosity of water. That is also a true statement. And finally, C, magnitude of V depends on the mass of the bunch. If you look at equation number 1, magnitude of velocity is related to the mass of the bunch. Look, there's m over there. So statement C is also true. Magnitude of V depends on the mass of the bunch. So all three statements are true. As a result, the correct choice should be choice number 5. All A, B, C, all A, B, and C are true. So that's how you solve this problem.